we have started by talking about electric forces. The electric force between two charged particles is equal to K, which I can now, because I've talked briefly about Gauss's law, write as 1 over 4 pi epsilon naught times Q1, Q2, divided by the distance between those two forces squared, times the radial vector r. Now, the next thing that we did was I generalized this. Okay, well, what's the electric field in a part of space due to just one point charge? Well, that's equal to 1 over 4 pi epsilon naught times q over r squared, radially outward. How does a point charge affect space such that if I put another charge there, then I could find the electric field? Well, if I have an electric, suppose I've got a case where I have, here is a point charge, capital Q. One thing that we use capital letters for in this course is that sometimes if I want to say, darn it, this thing is fixed, at least for this problem, I use a capital letter, whereas if I want to look at some parameter that might change, I'll use a lowercase letter. Suppose in this case I've got Q, and this Q is fixed. Now, if I bring in another charge, Q, lowercase q, there's going to be a force that force Q exerts on force lowercase q. Which means that if Q is free to move, at some point that force will cause point charge Q, lowercase q, to accelerate away, which means that at some later point it will have a velocity and a lesser charge acting on it. Now, in the first semester, we looked at this in terms of energy, and we're going to do that again. So, if I look at this, the work done is equal to be strictly correct, the integral of the force integrated over the path. Now, in this case, I've got a point charge moving directly away from another point charge. So here, for this case, well, the force, I could write this as Q times the electric field with a fixed point charge times dr, or Q is constant. The electric field of that point charge is 1 over 4 pi epsilon naught times Q over r squared dr. And I could find the work done in that case. Now, if I find the work done, from last semester, I can speak of if this is a conservative force. And yes, it turns out that the electric field, the electric force is indeed a conservative force if you store energy into this. If I throw a point charge at another point charge, it will slow down, removing kinetic energy or energy of motion from the system, but I'll get all that energy back when it comes bouncing away. So the electric force is a conservative force, which means I can speak of a potential energy system, and the work is equal to the opposite of that potential energy. Now, that's not Sure, that's helpful, but I want to do something better than that, because where I want to go with that is I want to be able to say, okay, suppose I don't know this second point charge. Suppose I don't want to recalculate this each time I have a point charge. Then I want to look at, I want to look at, how does the fixed charge affect the system? I mean, if I look at it like this, I'll have the work done is equal to, okay, Q over 4 pi epsilon naught times capital Q, because that's constant, that comes out. The integral of dr over r squared is negative one over r. So I then have to evaluate this between R1 and R2. Okay. That's, not that hard. If I take this to where, say, let R2 be infinitely far away, then the work done is equal to the opposite in the change in potential, which here, for a point charge, is equal to negative lowercase q times capital Q over 4 pi epsilon naught R1. So that depends on lowercase q and capital Q. But suppose I take this and I rewrite this such that I say that the work is equal to, well, let's take the dependence of that test charge out. So I could put any old charge in. So that's equal to Q times for a point charge, Q over 4 pi epsilon naught R1. And let me define the electric potential V for a point charge as 1 over 4 pi epsilon naught Q over R1. Now, the units of the electric potential are the units of, well, they're the units of work, or joules, divided by the units of charge, or coulomb. And I'm going to define that, that's going to be useful enough, so I'm going to define that as 1 volt. Now, electric potential is the one case in our books where the abbreviation for the unit, capital V, is the same as the name for the variable itself, capital V.